Algebra of sets. These are, see, what do you mean by algebra? Operational science. That is the branch of mathematics which deals with all operations is nothing but called algebra. Algebra of sets. It deals with set of all operations on sets. Algebra of matrices deals with all operations on matrices. Algebra of vectors deals with all operations, addition, subtraction, cross product, dot product, like that. Algebra of vectors. Of course, here we are ready to deal with the heading Algebra of sets. Means this branch of mathematics which deals with all operations on sets. How many operations are there? They're very familiar. First of all, union of sets, A union B. What is this? Set of all x's such that x belongs to A or x belongs to B. And if you want to represent this diagrammatically, such diagrams are being introduced by a famous mathematician called Venn, diagrams. A, B. In these diagrams, every set will be represented by a circle, a circular type arrangement, and the universal set is represented with a rectangular box. Okay, this box is universal set A, B. This is A union B. The shaded region entirely gives the set A union B. And then what is A intersection B? What is A intersection B? Set of all x's such that x belongs to A and x belongs to B. This is what you say about A intersection B, and diagrammatically we represent A intersection B like this. This is A intersection. The next operation before us is A minus B is equal to set of all x's such that x belongs to A and x does not belong to B. All those elements which are in B must be deleted from A if at all they are present in A also. What I mean to say is, it will be very clearly understood by means of the Venn diagram. This is A, this is B. A minus B. You have to first enter into A. Okay, we have entered, and you delete B. If at all a part of B is there, you delete this. After deleting it, what is remained here? This is the portion remained. This is the portion. What can you say about this? A minus B. What is this? A minus B. Well, you represent this region using dots. What do you say about this region? B minus A. That is B minus A. Well done. There has been another concept called A delta B. This A delta B is of course called symmetric difference of A and B. Symmetric difference of A and B. Of A and B. It is of course defined as A minus B union B minus A. So what is A delta B? What is A delta B? Both A minus B and B minus A. Their union is of course A delta B. And if you want to represent this diagrammatically, this is A delta B. This portion and this portion comprise A delta B. That is the symmetric difference of A and B. Okay, there is one more concept left behind. We shall look at that. The next concept before us is complement of a set. Now look here. This is the universal set and this is A. And all that portion which does not belong to A, that is outside of A, is of course called, it is just nothing but called, you observe this region is of course a complement or A dash or mu minus A. This is mu minus A. So, from the diagram itself, we can see and we can recollect the definition of a complement. Complement is denoted by either A complement, or this is read as A dash and this is read as A complement, and both of them are of course divided and defined by mu minus A. And this is the portion regarding A dash in a diagrammatical view, that is in Venn diagrams, that is A dash. Well, next one. Well, there are certain famous facts in set theory. Let us recall all those facts one by one. First of all, regarding inclusion, A is a subset of A, phi is a subset of A. Always. A is a subset of mu. Always. Phi is a subset of mu. Mu is always a subset of mu. Okay, and then the facts in which unions are involved. A is a subset of A union A. Of course, A union A is equal to A. A is a subset of A union B. B is a subset of A union B. A union B union C is equal to A union B union C. Some of them are named in different ways also. This is of course called idempotent law. Idempotency. In matrices you might have come across that particular word. When can you say that a particular square matrix A is idempotent? A square is equal to A, isn't it? Here in set theory, A union A is equal to A is an idempotent law. Similarly, A intersection A is equal to A is also idempotent law. And this is of course associative law. These are the things, rather facts in which union is involved. Next, let us now consider some of the facts in which intersection is involved. A intersection A is equal to A. A intersection B is subset of A. A intersection B is a subset of B also. Isn't it? And it is very clear if you can observe this intersection. A, B. What is this intersection? This is a intersection B. It is a part of A. It is a part of B also. Hence both of these are correct. One more thing, A intersection B is equal to B intersection A. This is called commutative law. Just like this, here also, A union B is equal to B union A. This is also commutative law. And then associative law with respect to intersection is also there. A intersection B intersection C is equal to A intersection B intersection C. These two are associative laws. These two are commutative laws. These two are idempotent laws. Yes. Well, there are some more facts. Let us observe them. Next one. A union B intersection C is equal to A union B intersection A union C. And in a similar way, A intersection B union C is equal to A intersection B union A intersection C. These two are of course called distributive laws. What are they called? Distributive laws. And regarding different subsets, A minus B union C is equal to A minus B intersection A minus C. A minus B intersection C is equal to A minus B union A minus C. A union B whole dash is just nothing but mu minus of A union B, isn't it? This is nothing but A dash intersection B dash, and A intersection B whole dash is equal to A dash union B dash. All these laws together called De Morgan's laws. They're called De Morgan's laws. The next one, if A is a subset of B, then A union B is equal to B. A intersection B is equal to A. Basing on this, A intersection A union B. A is a subset of A union B. So their intersection is the small set A. Again, A union A intersection B is also A. These three are called, specially called, absorption laws. Are called absorption laws. Good. And then disjoint sets. What do you mean by disjoint sets? When there is no joint, that is when there is no common portion, then they are called disjoint sets. That is, A comma B are disjoint if A intersection B is equal to phi. Well, there are again beautiful properties of these disjoint sets. What are they? Look here. How can you guess or how can you represent this disjoint C among sets A, B? Is there any common portion? No. Good. From the diagram itself, what can you say? A intersection B is equal to phi. A minus B is equal to, we have entered in A and we have deleted all the portion that belongs to B. There is no such portion. That is, there is nothing to be deleted. You will be going to have A. Similarly, B minus A is equal to B. A is a subset of B dash. How can this be true? You imagine? This is B. What is B dash? That portion which entirely does not belong to B. And in this portion, only A lives. So A is a subset of B dash. And in a similar fashion, B is a subset of A dash. B is a subset of A dash. These are all the consequences of disjoint sets. So all these conditions are equivalent. If one thing is given, all the other things can be obtained. If A intersection B is equal to phi, what happens? A minus B is equal to A. If B minus A is equal to B, what happens? A intersection B is equal to phi. If A is a subset of B dash, what happens? A intersection B is equal to phi, like that. Good. These are the properties of disjoint sets. And then A minus B can again be taken as A intersection B dash. What do you mean by A minus B? A and not B. Just like that, what is A intersection B? A and not B. B dash means not B, isn't it? Okay. Basing on this, A minus B union B minus A can be taken as A intersection B dash union A dash intersection B. Well, if you have the diagram, this is A, this is B, this is of course A minus B, this is of course B minus A. A delta B is equal to A minus B union B minus A. We know, of course, this shaded region can again be observed as A union B minus A intersection B, isn't it? So this again can be taken as A union B minus A intersection B. Altogether, how many forms of expression are there for A delta B? You observe all these. A union B minus B union A, A minus B union B minus A intersection B dash union A dash intersection B, A union B minus of A intersection B, like that. Three types of expression is possible to write A delta B. That is what we say about symmetric difference of A and B. What is A delta B? Symmetric difference of A and B. Good. And this could be possible by the observation A minus B is equal to A intersection B dash. A intersection B dash. That's good. The next concept. A union B minus A. A union B minus B. A minus A intersection B. A B minus A intersection B. A minus A minus B. B minus B minus A. These are straight and simple questions, and the way to answer them is, the best procedure is to use Venn diagrams. Let us answer this question. A, B, this is A, this is B, this is entirely A union B. From this, A has been deleted. What is there? This portion will be remained. From A union B, A is deleted. This portion will be remained. What is that portion? B minus A. If from A union B, if B is deleted, B is deleted. What portion is remained? This portion is remained. What is this portion? A minus B. Good. What is A minus A intersection B? From A intersection B is deleted. What is remained? A minus B. Good. From B, A intersection B is deleted. From B, this portion is deleted. This portion is remained. And what is that? B minus A. What is A minus of A minus B? In our usual algebra, A and A will be cancelled, leaving you B. But the answer here is not B. Why? Because these are not usual numbers. These are sets. So from A, this portion is deleted. This portion will be remained. What is nothing but A intersection B. Just like this, B minus of B minus A. What can you say? From B, B minus A is deleted. What remains is B intersection A or A intersection B or A intersection B. These are the famous results that can be viewed by making use of a Venn diagram. Next, you please observe that these two sets, phi and mu. Phi is an empty set with no elements, and mu is the universal set, the superset of all the sets under consideration. These two are of course called universal bounds in set theory. Okay, and there are certain properties mixed with these two involving complements also. What is that? A union A dash is mu. A intersection A dash is phi. Phi dash is mu. Mu dash is phi. These can be called properties of universal bounds. And not only that, A dash whole dash is A again. This is A dash whole dash is A. These are the elementary properties, and we shall come across some more important results while solving some objective type questions in the next session. And then regarding order of finite sets, if there are two or more number of sets, finite sets at our disposal, we have had some formula regarding order of sets, that is n of A union B, n of A intersection B, like that. What is that? N of A union B is equal to n of A plus n of B minus n of A intersection B. And these two can be transferable to this side and that side. Then what happens? N of A intersection B is equal to n of A plus n of B minus n of A union B. N of A union B. Good. You bring this to this side. What happens? N of A union B plus n of A intersection B is equal to n of A plus n of B. These are all very, very, very useful, very, very ancient, very, very important results. Good. One more thing is there. If n of A union B union C is required, then all sets taken one at a time. That is n of A plus n of B plus n of C. Now sets taken two at a time. N of A intersection B, n of B intersection C, n of C intersection A, and taken all the three at a time, n of A intersection B intersection C. Not only for 3 sets, for any number of finite number of sets, say n of A1 union, A2 union, A3 union, etc. An can also be taken like this. All the cardinalities of sets taken 1 at a time minus those taken 2 at a time plus those taken 3 at a time minus taken 4 at a time and so on. That will be the process of obtaining the cardinality. Yes, these formulae will help us a lot, and at the end of this topic we shall now go through another important and crucial portion regarding n of A union B and n of B A intersection C, like that. Next, we know that n of A union B is equal to n of A plus n of B minus n of A intersection B. Now, one thing is sure, n of A union B is less than or equal to n of A plus n of B always. Well, the question is the maximum number of elements of A union B and the minimum number of elements of A union B is the special case of interest in the present context. I think you would have understood. Maximum of n of A union B, minimum of n of A union B. How can you have it? Look here. Observe these sets that disjoint. What is n of A union B? N of A plus n of B. Now observe this case. Now you tell me, n of A union B, if you proceed from this case to this case, n of A union B decreased or increased? Decreased. Minus something, some intersection is there. Observe this diagram. N of A union B is further decreased. Why? N of A intersection B, n of A plus n of B minus something. Now you observe this case. N of A union B is further decreased. Is there any case of further decrease? No. So what is the minimum number of elements of n of A union B? This big set is easy. This is n of A union B, isn't it? Well, this is the minimum and this is the maximum. Maximum number of n of A union B exists if and only if A comma B are disjoint. Am I correct? Minimum number of A union B somewhat increase, somewhat increase, somewhat increase, full increase. So this is the maximum number of A union, n of A union B. And maximum value of n of A union B is equal to n of A plus n of B. This is the most beautiful concept that one must remember in one's mind. When can n of A union B will be maximum? When can n of A union be maximum? It is maximum if and only if A and B are disjoint. A and B are disjoint. And maximum number of elements in that particular case, what is that? N of A plus n of B. Good. Now, let us think of minimum value of n of A union B. Minimum of n of A union B exists if and only if, come on friend, observe the case. In which case you have the minimum number? This is the case with minimum number of elements in n of A union B. And that happens if and when and only when A and B are comparable. And in this case, minimum number of n of A union B is therefore equal to, what is n of A union B here? If this is A, n of A is the answer. If this is B, n of B is the answer, isn't it? Therefore, this is minimum of n of a and b is equal to maximum of n of a comma n of b. A and b are comparable. Who knows it? Whether A subset of B or B subset of A. If A is a subset of B, A and B is B. N of A and B is N of B. If B is a subset of A and B is equal to A. N of A and B is N of A. So in either case, the maximum of N of A and N of B becomes minimum of N of A union B. So my dear friend, please do not get confused of it. You please get concentrated carefully on the concept. So in this, we could have had a very good discussion about maximum of N of A and B and minimum of N of A and B. That's it. Now this is our turn to look at maximum of N of A intersection B and the minimum of N of A intersection. Yes. Now, we shall look at maximum of N of A intersection B and minimum of N of A intersection B. Observe here these diagrams. What is N of A intersection B? 0. Here something increased, further increased, full increase. What is N of A intersection B? Here this is A intersection B, isn't it? This is A intersection B. So out of all these diagrams, you can easily tell when can N of A intersection B be maximum in this case. What is this case? A and B are comparable, isn't it? So maximum of N of A intersection B exists if and only if A and B are comparable, are comparable. That is either A subset of B or B subset of A. And in this case, maximum of N of A intersection B is therefore equal to, come on friend, you can tell me. What is N of A intersection B? This or this? The interior part, isn't it? Hence, it can be taken as minimum of N of A and N of B. This is beautiful. Well, we have discussed about the maximum number of N of A intersection B, the maximum value of N of A intersection B. Now, let us take interest in noting down the minimum value of N of A intersection B. Good. Minimum of N of A intersection B. When can it happen? If you move from this diagram to this diagram, N of A intersection B is decreased, still decreased, full decrease. Actually, it is 0, isn't it? So, what is the minimum number? Purely 0. Therefore, minimum of N of A intersection B exists if A and B are disjoint. A and B are disjoint. And in this case, minimum of N of A intersection B is equal to 0. How much? 0. That's it about the minimum value and maximum value of both N of A and B and N of A intersection B.